Come on, my dears, let us begin chapter number 4, bit lengthy chapter and worth understanding, is very useful from syllabus point of view. Let us begin with the preface, with the introduction. As such, nothing is being asked in the examination from preface or introduction, but we should not take any chance. So let me clear some points in the introduction. First, failure of ray optics. There is a branch of physics in which it is assumed that light energy propagates rectilinearly in the form of a ray. Such a branch is called ray optics. Ray optics simply fails in explaining 5 optical phenomena. They are interference, diffraction, polarization, transmission and holography. Interference, diffraction, polarization we will study in this chapter. Okay? Transmission, you know, if light ray happens to just emerge from a given medium, that process is known as transmission, just to get through. Okay? And about holography, you will study in your higher studies. Okay? These 5 phenomena cannot be explained using ray optics. This fact gives you failure of ray optics. Then history says that in the year 1678, it was Mr. Huygens who had introduced wave theory for propagation of light. He assumed that light energy propagates in the form of waves. Such a theory is called Huygens wave theory. Huygens wave theory succeeded in explaining phenomena like reflection and refraction very nicely. Using wave theory proposed by Huygens, you can explain phenomena like reflection and refraction satisfactorily. Okay, fine. Then history says that in the year 1801, it was Mr. Thomas Young who had explained optical phenomenon called interference using Huygens wave theory. And then in the year 1815, it was Mr. Fresnel who had proposed wave theory for rectilinear propagation of light. For rectilinear propagation of light, the wave theory was proposed by Mr. Fresnel in the year 1815. Fine. Then in the year 1808, Mr. Malus had invented new phenomenon which is called polarization. Now, using Huygens theory, this polarization cannot be explained. Why? Because Mr. Huygens was believing that light energy propagates in the form of longitudinal waves. Light energy propagates in the form of longitudinal waves. But this polarization is such a phenomenon which is possible only for transverse waves. And for light waves, polarization is possible, meaning thereby light waves must be transverse, must not be longitudinal as assumed by Mr. Huygens. So, because Mr. Huygens had believed that light waves are longitudinal, he could not explain this phenomenon which is polarization. Okay, fine. That was his mistake. Okay, fine. And one more thing, for the propagation of longitudinal waves, because they are mechanical waves, we require some elastic medium for their propagation. Fine. But you know, light waves, they can pass through even vacuum. In the absence of medium also, they can propagate. So light waves actually were not longitudinal, they are transverse only. But when the things were not known to these scientists, they believed that light energy propagates in the form of longitudinal waves. But for propagation of longitudinal waves, some medium is required. So that medium was assumed by scientists with the name Mr. Mr. Young and Mr. Fresnel. Mr. Young and Mr. Fresnel, they also had supported to Huygens wave theory. They altogether had imagined one medium called ether. The name of that medium was ether, and they had imagined this medium everywhere. Okay, so universally they had imagined some medium called ether in which these light waves can propagate through longitudinal waves. That was their imagination only. Fine. Now history says that this polarization, actually it was proved by Mr. Michael Faraday that polarization is due to very strong magnetic field in the light waves. So light waves were assumed to be electromagnetic, and that assumption was first made by Mr. Michael Faraday. Historically, he had made this assumption first, that light waves perhaps may be electromagnetic. Fine. And then Mr. Maxwell, he had made the study of laws of electromagnetism. He had compiled all these laws and he made this study, he described this study in the form of 4 Maxwell differential equations, and that theory was known as Maxwell's electromagnetic theory, in which light waves were assumed to be electromagnetic waves of very high frequency. Yes. Then after this assumption, what Mr. Maxwell had made, that light waves are electromagnetic waves of high frequency, it was their theoretical assumption only, but practically it was not proved by them. Practically it was proved by Mr. Hertz in the year 1887. In the previous chapter, we have studied Hertz experiment through which we could establish that yes, light waves are electromagnetic waves, they can be generated in laboratory. Okay. So very first practical evidence was given by Mr. Hertz regarding production of electromagnetic waves in the year 1887. Then Mr. Michelson and Mr. Morley, in the year 1887, they had performed one experiment. Later on, that experiment became very famous all over the world with the name ether drift. And through this experiment, they had proved that there is no existence of such medium. There is no existence of ether. Ether was simply ideal imagination only. There was no existence of such a medium. And now, finally, in physics, we have prepared one branch called scalar wave optics, in which oscillations of electric and magnetic field during the propagation of light wave are considered in the form of a definite scalar, and such a branch is called scalar wave optics. Okay. Come on, my dears, let us proceed further. But before that, I would like to introduce 2 words because they are going to be used repeatedly. So let us be clear about what they mean. First is what is called homogeneous medium. A medium in which given physical property is same at all the points is called a homogeneous medium. I repeat, if a given property is same at all the points in a given medium, then that medium is called homogeneous medium. Fine. And what is called isotropic medium? If a given physical quantity is same in all the directions in a given medium, then that medium is called an isotropic medium. I repeat, if a given physical quantity is same in all the directions in a given medium, then that medium is called an isotropic medium. Fine. Medium of air we will consider now onwards to be homogeneous, isotropic, and always 3-dimensional. Come on, homogeneous, isotropic, and 3-dimensional. Okay, fine. Now let us study one concept, what is called wavefront. Let us see. To understand very clearly about wavefront, you please consider 4 thin strings kept parallel to each other and under proper tension. One string you may fix over here, one here, and one here. Okay. So hold 4 strings this way, correct? There one end you have fixed here, and here. Okay. Just hold them like this, and then you give oscillations this way. When you are giving oscillations this way, you are producing disturbances. And when the disturbances are produced, you know they will move away from the source. So when these disturbances travel along the length of the strings, you just consider 4 particles which are shown in the diagram by symbols A, B, C and D. Fine. Now look in the figure carefully. You will find at a given point of time, this particle has been displaced vertically upwards, and suppose it has undergone this much maximum displacement in upward direction, and because of that there has been crest which is formed in this much part of the string. At the same moment, suppose there is a crest formed here also, and here also, correct? Now in second semester you have studied, whenever simple harmonic oscillator moves from equilibrium position to the positive end of the path, its phase becomes pi by 2 radian. So when this particle has come over here, its phase has become pi by 2 radian. Similarly, phase of this particle is also here pi by 2 radian, for this also pi by 2 radian, for this also pi by 2 radian. I mean to say, these all 4 particles have phases of oscillation same equal to pi by 2 radian. Now during the downward oscillation, they oscillate downward also simultaneously. They all will come down, they all will undergo maximum displacement in downward direction simultaneously, and at that time here, instead of crest, here trough will be produced. But at a given point of time, if trough is produced here, then here also, here also, here also. I mean to say, for all these 4 particles A, B, C and D, they oscillate simultaneously vertically upwards also, simultaneously vertically downwards also. They oscillate with the same phases. Now just imagine one surface which is passing through such 4 particles which are oscillating with the same phase. Such an imaginary surface is only known as wavefront. How would you define it? An imaginary surface passing through the particles oscillating with the same phase is called a wavefront. An imaginary surface passing through the particles oscillating with same phase is called wavefront. I repeat, an imaginary surface passing through the particles oscillating with same phase is called a wavefront. After some time, it will so happen that these disturbances will travel ahead and they will come at these 4 particles, say P, Q, R and S. Now it is turn for these 4 particles to oscillate simultaneously. We find crest is formed here, here, here and here at a time, meaning thereby these 4 particles are oscillating with the same phase. An imaginary surface passing through the particles oscillating with same phase is called a wavefront. Earlier wavefront was here, now it is here. Later on, after some more time, it may be here, then here and so on. I mean to say, in these strings, when the wave propagates ahead and ahead, we find as if these wavefronts are also moving ahead and ahead. That is why, for the sake of convenience, sometimes propagation of wave is described by motion of wavefronts. Propagation of wave is described by motion of wavefronts. Okay, fine. In 3 dimensions, there are 3 main types of wavefront. One is called spherical wavefronts, second is called cylindrical wavefronts, and third one is called plane wavefronts. Let us see about them one by one. First of all, we talk about spherical wavefronts. Okay. Consider a point-like source. Point-like source. How do you prepare a point-like source of, say, light waves? How would you prepare? Just take one bulb, put it in a box which is enclosed from all the sides, and then just prepare a very small hole in one of the sides. You switch on that bulb, light energy would come out. When it comes out of very small hole, at that time that hole can be taken as small point-like source of light waves. Okay? And then from such point-like source of light waves, we find that whichever wavefronts are emitted, they are having spherical shape. Correct? Because their shape is like a part of a sphere, we call such wavefronts as spherical wavefronts. Okay? How would you define them? Wavefronts emitted from a point-like source and then propagating in three-dimensional homogeneous isotropic medium are having shape of sphere, spherical surface, and hence they are called spherical wavefronts. Wavefronts emitted from point-like source and then propagating in three-dimensional homogeneous isotropic medium are found to be having spherical shape, and hence they are called spherical wavefronts. I repeat, wavefronts emitted from point-like source and then propagating in three-dimensional homogeneous isotropic medium are found to be having spherical shape, and hence they are called spherical wavefronts. Correct? In the diagram, you will see some lines are drawn in the direction of propagation of wave. Not only that, they are perpendicular to wavefronts. Such lines are called rays. Lines perpendicular to wavefronts and showing direction of propagation of wave are called rays. But because these rays are going away from each other, we call them diverging rays. We call them diverging rays. Fine. So in case of spherical wavefronts, remember, rays are always diverging. Waves having spherical wavefronts are called spherical waves. Waves having spherical wavefronts are called spherical waves. Fine. Now we go for cylindrical wavefronts. Just make one difference. Instead of point-like source, now you please consider linear source. Correct? And say from this linear source, which is having cylindrical shape, the shape of the source itself is cylindrical, then wavefronts emitted from it also have same shape, that is cylindrical wavefronts. Okay? Fine. How would you define cylindrical wavefronts? Wavefronts emitted from linear source and then propagating in three-dimensional homogeneous isotropic medium are having shape of a cylinder, are having cylindrical shape, and hence they are called cylindrical wavefronts. I repeat, wavefronts emitted from linear source and then propagating in three-dimensional homogeneous isotropic medium are having cylindrical shape, and hence they are called cylindrical wavefronts. Fine. In case of these cylindrical wavefronts, how would you draw rays? I am showing you. Rays are those lines which are perpendicular to wavefronts. If you draw perpendiculars in one direction, say perpendicular to this part of the cylindrical wavefront, then all these rays you will find mutually parallel. But not necessary that every time you should draw perpendicular lines in this direction only, not necessary. You may draw in all the directions, correct? You may draw perpendiculars in all the directions for the remaining parts also. If you do that, then you will find rays like this, correct? Which are lines perpendicular to other parts of the same cylindrical wavefront. And now, if you look at all these rays at a time, then because they are going away from each other, they are said to be diverging. They are said to be diverging. So remember, for cylindrical wavefronts, rays are parallel in one direction, but diverging in all directions. Okay, and then wavefronts, if they are cylindrical, then waves are called cylindrical waves. Waves having cylindrical wavefronts are called cylindrical waves. Fine. Let me repeat the definition of cylindrical wavefronts. Wavefronts emitted from linear source and then propagating in three-dimensional homogeneous isotropic medium have cylindrical shape, and hence they are called cylindrical wavefronts. Fine. Now we go for plane wavefronts. In case of plane wavefronts, you may take either point-like source or linear source, but most important condition is that you must think of such wavefronts at infinite distance from the source, and that too locally in the limited part. See, as you move away from the source, you can see here size of wavefronts grows, increases. Then if you think of infinite distance, then at infinite distance from the source, it will so happen in the limited part of a wavefront, if you see, you will find it flat, planar, and that's why such wavefronts are called plane wavefronts. Fine. How would you define them? Wavefronts emitted from point-like or linear source and then propagating in three-dimensional homogeneous isotropic medium are found to be plane locally at infinite distance from the source, and hence they are called plane wavefronts. I repeat, wavefronts emitted from point-like or linear source and then propagating in three-dimensional homogeneous isotropic medium are found to be plane locally at infinite distance from the source, and hence they are called plane wavefronts. In case of these plane wavefronts, you can see in the diagram, the rays are mutually parallel. The rays are mutually parallel. Fine. Waves having plane wavefronts are called plane waves. Waves having plane wavefronts are called plane waves. Fine. Now let us study what is called Huygens Principle. In order to explain the propagation of light waves, Mr. Huygens had proposed one principle called Huygens Principle. You know what is its physical importance? Using Huygens Principle, we can construct the shape and position of new wavefront geometrically, correct? Let us see how. First of all, let us see Huygens Principle, statement of Huygens Principle. Consider this xy as cross-section of some spherical wavefront taken parallel to the plane of the figure. So xy is given wavefront, okay? Now just consider some points on it. Here I have considered only 3 points, say point A, point B and point C. Mr. Huygens had proposed that each and every point or particle on any wavefront behaves like self-independent secondary source, and it emits secondary spherical waves. After infinitesimal small interval of time, means after very small time, the surface circumscribing means tangential from outside, surface circumscribing to all these secondary spherical waves gives us shape and position of new wavefront at that time. This very statement is called Huygens Principle. I repeat, each and every point or particle on any wavefront behaves like self-independent secondary source, and it emits secondary spherical waves out of it. Full stop. After infinitesimal small interval of time, a surface circumscribing to all these new secondary spherical waves gives us shape and position of new wavefront at that time. Full stop. This very statement is called Huygens Principle. Now last time, each and every particle or point on any wavefront behaves like self-independent secondary source, and it emits secondary spherical waves out of it. full stop. After infinitesimal small interval of time, a surface circumscribing to all these spherical waves gives us shape and position of new wavefront at that time. This statement is called Huygens Principle. Now, let us construct geometrically the shape and position of new wavefront from a given wavefront after a very small time. Suppose this is the cross section of spherical wavefront taken parallel to plane of the figure. Fine. That is xy. It is at time t. Now take some points on it. Okay. Say points A, B and C. Now taking these points at centers and then after taking this much radius. Radius is this much distance traveled by the spherical wave. It is distance, it is constant velocity into time. Constant wave velocity I am taking v, time interval I am taking delta t. So this much is the radius of this sphere. By taking this much radius, which is v delta t, you should prepare imaginary spheres. Fine. And now a surface which is tangential to these spheres will give you shape and position of new wavefront. Now for such spheres, you may have two tangential surfaces, one from outside, from outer side, and one from inner side, correct? If you draw two tangential surfaces, x dash y dash also, and x double dash y double dash also, one from outer side, one from inner side, then indirectly it indicates that light wave or any other wave would propagate away from the source also and towards the source also. No. In practice, any type of wave always propagates away from source. It never propagates towards the source. Then this fact gives you limitation of Huygens principle. Why any wave does not propagate towards the source? This fact cannot be explained using Huygens principle. This fact gives you limitation of Huygens principle. Then who had explained it properly? There were two scientists, Mr. Voigt, G is silent. G is silent, you should pronounce Mr. Voigt and Mr. Kirchhoff. They had explained the reason why any wave does not propagate towards the source. Why? What is the reason? See the reason now. Look, consider this as a main source, primary source. This is the wavefront emitted from it, and this is the normal or perpendicular drawn in the forward direction. Okay. Now with this normal drawn in the forward direction, if any given direction makes angle theta, then in that particular direction, what is the intensity of wave propagating in that direction? That was found by these two scientists, and the result is this, that intensity is directly proportional to cos square theta by 2, where theta is the angle made by given direction with the normal drawn in the front direction. Okay, fine. Now we are interested in finding out why any wave does not propagate towards the source. So at present our direction of interest is not this, direction of our interest is this, and this direction of our interest makes this much angle with this normal drawn in the front direction or in the forward direction. Now this angle you can see in the diagram, this much angle is pi radian. So at present theta is pi radian, put it here. Put theta equals to pi, pi by 2 will be, cos pi by 2 will be 0, cos pi by 2 will be 0. In short, I will be 0, meaning thereby intensity of wave propagating towards the source would be 0. That is why any wave does not propagate towards the source. Okay, all the waves definitely propagate always away from source, never towards the source. But this expression was not given by Huygens. This fact gives the limitation of Huygens principle. Okay. Then let us talk about case of plane wavefront. Say this xy is the cross section of plane wavefront taken parallel to the plane of the figure. And now take some points on it, say points A, B, C, taking these points as centers and taking this much radius, you are supposed to prepare imaginary spheres. And now for these spheres, you can draw tangential surface in both the directions, front as well as rear. This is the tangential surface drawn in the front direction, and this is the surface drawn in the backward or rear direction. But just now I explained to you, no wave propagates towards the source, all the waves propagate away from the source. So we should consider this tangential surface, that is x dash y dash, which will give you shape and position of new wavefront after delta t time. Have you noticed one thing? If original wavefront is spherical, then new wavefront is also spherical. If original wavefront is plane, then new wavefront is also plane. Okay? In case of propagation of waves through isotropic medium, remember the shape of wavefront is sustained, is remaining as it is. Okay? Fine. Come on, my dears. Look, we are proceeding further in chapter number 4. You know, Mr. Huygens, he had given one theory which is called wave theory. He had assumed that light energy propagates in the form of wave. Correct? Now, using this Huygens wave theory, we can explain phenomena of reflection of light as well as refraction of light very nicely. Let us see how this phenomena can be explained, and then after we will be just deriving one law of reflection and another Snell's law for refraction of light. Okay? Let us take them one by one. First of all, let us try to understand reflection of light using Huygens wave theory. Look, we have one reflecting plane surface. Plane reflecting surface, say AB. Fine. On this plane reflecting surface, we just make a plane wave front PQ incident this way. Correct? It is made incident this way. It is made incident on this reflecting face AB such that at time t equal to 0, point P on this wavefront simply touches this reflecting face. At time t equal to 0, point P simply touches this reflecting face. Fine. Now tell me, this is incident wavefront, which is plane wavefront. It makes angle QPR with a reflecting face. Angle made by incident wavefront with the reflecting face is known as angle of incidence. Let it be small I. So angle QPR is going to give you angle of incidence. Let it be shown by symbol small I. Okay. Now, how is the shape and position of new reflecting wavefront at time t? That is what we have to find out. Incident wavefront we know. Now we have to find out reflecting wavefront. Correct? Come on. Where will be reflected wavefront? At which position? With what shape? That is what we have to find out. Look, from t equal to 0 onwards, you know all these points, because they are situated on wavefront, according to Huygens principle, any point on any wavefront behaves like self-independent secondary source, and it emits secondary spherical waves out of it. Okay, fine. So all these points, all these points will start emitting secondary spherical waves. So as we proceed from point P to point Q, all these points, when they behave like self-independent secondary sources, will start emitting secondary spherical waves, and those waves are made incident on this reflecting phase. Fine. So, as we proceed from point P to point R, all the points coming sequentially, coming consecutively, will receive light energy one after another. Correct? Fine. Turn by turn, these all points will receive light energy. Fine. And then after, those light waves will start getting reflected from all these points. Fine. Now, this very point started behaving like self-independent secondary source right from instant t equal to 0, because at time t equal to 0, it itself is on wavefront. And when it behaves like self-independent secondary source, naturally it will emit secondary spherical waves in all the directions. Let the emission continue for t time. In t time, how much is the distance traveled by secondary spherical wave? If it travels with velocity v, then distance traveled is given by constant velocity into time. Constant velocity into time. So these all distances are v into t. These all distances are v into t. Fine. Now, at the end of t time, if we just think of a surface which is tangential to all these secondary spherical waves, then it will give you shape and position of new wavefront emitted from point P at the end of t time. The way you are getting new wavefront from point P at time t, same way, if you try to find out new wavefront at time t from point t1, it will be this. At the end of same t time, if you try to find out new wavefront emitted from t2, would be this. Correct? Now, think of that surface which is tangential to all these new wavefronts at a time. Then that tangential surface is this, which is SR. So, this very tangential surface which is tangential to all these new wavefronts will give you shape and position of new wavefront at the end of t time. Correct? Now, this is known as reflected wavefront, and angle made by this reflected wavefront with this reflecting phase is known as angle of reflection, shown by symbol small r. Fine. Angle made by incident wavefront with the reflecting phase is called angle of incidence, and angle made by reflected wavefront with the reflecting phase is called angle of reflection, shown by symbol small r. Incident light ray is perpendicular to incident wavefront. Similarly, reflected light ray is perpendicular to reflected wavefront. Both these distances are travelled with the same velocity in same time, so they have to be equal. This is also v into t, and this is also v into t. This is distance travelled by incident light ray, this is distance travelled by reflected light ray. Okay, fine. Now tell me, if you compare two triangles, which two triangles? Triangle PSR and triangle RQP. Come on, triangle PSR and triangle RQP. Then you will notice that these two angles are equal because they both are right angles. Angle PSR and angle RQP. Angle PSR and angle RQP. These both angles are equal because they are right angles. Moreover, opposite to right angle will be hypotenuse. Here also opposite to right angle will be this hypotenuse. And because both the hypotenuse are same, you can say these two triangles have same common hypotenuse. Correct? And then whatever is this measurement, same is this measurement. So measurement of this side, that is QR, will be equal to this side, that is PS. So line segment PS equals to line segment QR or RQ, and both of them are equal to V into T. Both of them are equal to V into T. Now tell me, according to congruence, right angle, hypotenuse and side. According to congruence, right angle, hypotenuse and side. According to this congruence, these two triangles are identical. Which two triangles? Come on. PSR and RQP. Triangle PSR and triangle RQP, they are identical. And for identical triangles, don't you know, corresponding angles have to be equal. If I am taking angle here, say angle QPR, then here I should take angle SRP. So angle QPR should be equal to angle SRP, But what is angle QPR? Angle QPR is angle of incidence, that is I. What is angle SRP? Angle SRP, it is this angle which is small r. So we have proved that angle of incidence is equal to angle of reflection. This is nothing but law of reflection, which we have proved here using Huygens wave theory. Okay, fine. Let us prove now another important result, that is law of refraction called Snell's law using Huygens wave theory. Consider this as refracting phase. Which one? AB. AB is plane refracting phase which separates two media. Upper medium has, say, it is, say, suppose rarer medium having absolute refractive index, say N1, and the lower medium has absolute refractive index, suppose N2, which is denser medium. Because this second medium is optically more denser, then you can say N2 must be greater than N1. N2 must be greater than N1. Fine. Now suppose at time t equal to 0, plane wavefront PQ is made incident on this refracting phase such that at time t equal to 0, point P simply touches this refracting phase. And now tell me, angle made by incident wavefront with the refracting phase is called angle of incidence. Let it be shown by symbol small I. Now according to Huygens principle, each and every point or particle on any wavefront behaves as if it is a self-independent secondary source and it emits secondary spherical waves out of it. So think of emission of secondary spherical waves out of all these point-like sources which are now made incident on this refracting phase. Correct? So as we proceed from point P to point R, all these points receive light energy consecutively, sequentially, one after another, turn by turn. And now, right from t equal to 0 onwards, this point already started behaving like self-independent secondary source, started emitting secondary spherical waves in all directions. Look here, this way, in all directions. Fine. Now, at time t, the secondary spherical waves emitted from point P have reached here, correct? And then if you draw tangential surface, it would give you this new wavefront at time t emitted from point P. Similarly, at the end of same t time, if you find out new wavefront from point T1, it will be this. At the end of same t time, if you find out new wavefront emitted from T2, it would be this. And now just draw a surface which is tangential to all these new wavefronts, and that surface would be this. Again, it is a plane surface which gives you refracted wavefront, because it is in a different medium. Whenever wave changes medium of propagation, it goes from one to another medium, it undergoes refraction. That's why this wavefront is called refracted wavefront. Angle made by refracted wavefront with a refracting phase is called angle of refraction. Let it be shown by symbol R. Now, refracted light ray is perpendicular to refracted wavefront. Incident light ray is perpendicular to incident wavefront. This is the distance traveled by incident wave in t time, and because the distance is traveled in the first medium where velocity of wave is v1, this much distance would be constant velocity into time, that is v1 into t. Similarly, this is the distance travelled by refracted wave in time t in the second medium where wave velocity is v2. That's why this much distance is v2 into t. And now, come on, in triangle PQR, you just find out sine of I. Sine of I. Sine of I means opposite to I divided by hypotenuse. Opposite to I, it is QR or V1 into T. V1 into T. Divided by hypotenuse, that is opposite to right angle, which is PR. PR. Opposite upon hypotenuse. Correct? Now think of this triangle, triangle PSR, and find out sine of R. Sine of R means opposite to R divided by hypotenuse. Opposite to R, it is this much or V2 into T. V2 into T. Divided by hypotenuse, that is opposite to right angle, it is PR. PR. And now tell me, if you take ratio of sine I to sine R, this upon this, it will be equal to this upon this. And when you take this upon this, T will cancel, PR will cancel, giving you V1 upon V2. V1 upon V2. But ratio of velocity of wave in first medium to the velocity of wave in second medium is called relative refractive index of second medium with respect to first medium, shown by symbol n to 1. And by definition, you know from third semester, n to 1 is nothing but n2 upon n1. n2 upon n1. Correct? Now just take cross multiplication. n1 sin I equals to n2 sin R. n1 sin I equals to n2 sin R. Instead of I, because it is angle in the first medium, let it be shown by symbol theta 1. Because this is angle in second medium, let it be shown by symbol theta 2. Then this equation will be n1 sin theta 1 equals to n2 sin theta 2. n1 sin theta 1 equals to n2 sin theta 2. My dears, you know very well, it is nothing but Snell's law. So this is how we can derive Snell's law using this Huygens wave theory. Okay, fine. Now let us go for principle of superposition. One principle of superposition you had studied in third semester for finding out resultant Coulombian force exerted on a given point charge exerted by many other charges exerted by remaining charges in a given charge system. Correct? You want to find out resultant Coulombian force exerted on any one point charge out of a given system of point charges by rest of the point charges, then you can apply common principle of superposition. Similar principle we are going to study here for superposition of waves, not superposition of forces. Here we are going to consider superposition of waves. I am showing you how. Consider calm surface of water which is horizontal, and on that horizontal surface we just select this very particle, correct? Say particle P. Say particle P. So this is the particle P, correct? And at particle P, what we do, we just keep some spherical bob. We give it up and down oscillation, say with amplitude 1 centimeter. Okay? When you just give it oscillation up and down, we find that here water waves are produced. Now, the shape of water wave produced at some instant of time is suppose this. If shape of first water wave is this, it means to say that this particle has gone from here to here. When it has gone from here to here, you can see it has undergone 1 centimeter displacement in upward direction. 1 centimeter displacement in upward direction. Fine. Now, stop oscillating first bob. Stop it oscillating. And now think of second spherical bob, and when you give it up and down oscillation, then whatever is the shape produced on the water surface is suppose this. And this shape indicates that this particle has gone from here to here. When it has gone from here to here, let it be 2 centimeter, correct? In upper direction, 2 centimeter in upper direction. Now you do one thing, on this water surface, this is first spherical bob, say this one is second spherical bob, you give them oscillations at a time simultaneously. Okay? Here first wave is generated, here second wave is generated, here amplitude is 1 centimeter, here amplitude is 2 centimeter, and now both the waves will superpose on each other. When both the waves superpose on each other, then after there is no existence of first wave, no existence of second wave, now there is existence of only one, that is resultant wave, and that resultant wave is this, in which you can see the same particle has gone from here to here. When it has gone from here to here, this is the resultant displacement. It is found to be practically 3 centimeter in upward direction. Now tell me, this 3 centimeter in upward direction, can't you write this way? 1 centimeter in upward direction plus 2 centimeter in upward direction. Can you write? Yes. Now this is nothing but displacement produced by only first wave. This is nothing but displacement produced by only second wave. So these are independent displacements, and when there is a superposition of these two waves, then resultant displacement is found to be vector addition of these two displacements produced by superposing waves independently. This very equation is called principle of superposition. But not necessary that we should have superposition of only two waves. In general, you may have superposition of n number of waves, and in that case, in general, you can write the whole equation like this: vector E equals to vector E1 plus vector E2 plus dash 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 plus vector En. Now using this statement, using this mathematical form, you can give the statement of principle of superposition in words, something like this. I'll speak it out 2 to 3 times. You please try to pick up all the words, their meanings, and then try to remember also, please. Look, whenever there is a superposition of two or more than two waves at a given particle of medium simultaneously, then the resultant displacement produced in that particle is just equal to vector addition of displacements produced by the superposing waves independently. Full stop. This very statement is called principle of superposition. I repeat, whenever there is a superposition of two or more than two waves at a given particle of medium simultaneously, then the resultant displacement produced in that particle is just equal to vector addition of displacements produced by superposing waves independently. Full stop. This very statement is called principle of superposition. Last time now, whenever there is a superposition of two or more than two waves at a given particle of medium simultaneously, then the resultant displacement produced in that particle is just equal to vector addition of displacements produced by superposing waves independently. This statement is called principle of superposition. Okay. Now please remember this principle. We are going to apply it in the next period. Okay. Please remember.